Let's look at our first problem, problem number 78, subsets, difficulty level medium. Question reads as follows: given a set of distinct integers, nums, return all possible subsets. That means the power set. And comes with a hint. The solution set must not contain duplicate subsets. Comes with an example. Nums equals 1, 2, 3, and then the output should be basically the power set of all those numbers, meaning 3, 1, 2, 1, 2, 3, 1, 3, 2, 3, 1, 2, and the empty set. All right, let's have a look at the second problem pertaining to backtracking, subsets 2. This is LeetCode problem number 90, subsets 2, difficulty level medium. Given a collection of integers that might contain duplicates, nums, return all possible subsets. Again, the power set. And also, they say here, the solution set must not contain duplicate subsets. Here's an example where the number 2 is duplicate. It reads input 1, 2, 2. And then the output again should be 2, 1, 1, 2, 2, 2, 2, 1, 2, and the empty set. Note here, since we have the duplicate 2, it can appear also twice in the solution subsets, like 1, 2, 2, or 2, 2. Let's have a look at the third problem. Problem number 46, permutations. Given a collection of distinct integers, return all possible permutations. For example, here the input is numbers 1, 2, 3, and then the output should be all different permutations of these 3 numbers. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. That's basically all the different possibilities of how to arrange those 3 numbers. Let's have a look at the next problem pertaining to backtracking. That's LeetCode problem number 47, permutations 2. And its difficulty level is medium. Given a collection of numbers that might contain duplicates, return all possible unique permutations. Input 1, 1, 2. Output 1, 1, 2, 1, 2, 1, and 2, 1, 1. So that's all the possible unique permutations out of it without running into duplicates by seeing the same number twice at the same positions, so to say. Okay, let's have a look at the next problem pertaining to backtracking. 39, combination sum, medium. Given a set of candidate numbers, candidates, without duplicates, and target number, target, find all unique combinations in candidates, where the candidate number sums to target. The same repeated number may be chosen from candidates unlimited number of times. And then it comes with 2 hints. Note, all numbers, including target, will be positive integers, which is going to be important later. The solution set must not contain duplicate combinations. It comes with 2 examples. Number 1, input candidates 2, 3, 6, 7, and the target is 7. And the solution set is 7 and 2, 2, 3, summing up to 7. Second example, candidates 2, 3, 5, target 8. Then the solution set is 2, 2, 2, 2. So we got a duplicate of 2, 2, 3, 3, a duplicate of 3 and the number 2, and 3 and 5. Now let's have a look at the last problem pertaining to backtracking in our examples. 131 palindrome partitioning. Given a string S, partition that string S such that every substring of the partition is a palindrome. Return all possible palindrome partitioning of S. For example, input AAB, output AAB, and AAB. All right. So now the key thing is to find the underlying theme of which all those problems are a variation. And that underlying theme is that you have a vector list set of candidates and a given target. And you want to find all those combinations of candidates that might contribute to the solution of your target. That can be all of the candidates, that can be some of the candidates. But the goal of backtracking is to just go all the possibilities, all the possible paths, all the possible combinations of those candidates, plus some logic, like in the case of the palindrome, to apply. And then have a check if you have satisfied a condition for that subset of candidates to be an actual solution. And if so, then put the solution onto your vector of vector, or your list of lists, or your list of sets. And the underlying pattern can be really, really nicely summarized with 3 steps. That's been really, really nicely explained here in a blog by Mr. Alberto Arrigoni in 2018. Basically boiling down backtracking into 3 different steps. And I recommend going through this entire page line by line. But let's go straight to the key aspect here. And the key aspect is here to basically do 3 different steps. First step, choose. Select one number by adding it to the stack that holds the current branch. Or select one item from your list of candidates. Explore. Recursively call your helper function, explore helper, which will carry on the recursion and pass along the stack which contains those numbers. So that's why in most of those backtracking solutions, you will find another list or another vector of sub candidates. Not all of those candidates, but those that you currently want to explore, that are being passed along in explore helper. When you've chosen, you go down the current branch up until you hit your terminal condition, and then either you have satisfied your requirement for being a solution, then you add it to your list of solutions that are being generated by the candidates, or you were not able to find a solution, and then you still just go back. And when you go back, you do unchoose. You remove the recently added number and go back to step 1, which is choose, to explore another sub-branch. Here we get like another sentence on the termination condition. The termination condition that will stop the recursion and add the current branch to results list is given by the comparison between your expectation and what you put in as the amount of candidates. That's the logic that you put in your backtracking algorithm, that in our wide range of problems can be anything from permutations to finding combinations that lead to a sum to finding palindromic substrings. But the key thing here is that all backtracking algorithms basically function by the same pattern: choose, explore, unchoose. And in order to keep track of all that, you always pass along that additional variable iterator to know where you actually are within your set of candidates. So now that we have like the underlying theme, that's basically pertaining to all those different problems. Let's have a look at those solutions to all those problems that actually went with doing a backtracking approach. And we're going through those solutions one by one, and we'll see that all of those solutions basically follow those same patterns: choose, explore, unchoose. And that's all that. All right, let's go through the solutions for all the problems that we have looked at one by one, exploring the paradigm necessary for backtracking. And that paradigm is, to iterate again, choose, explore, unchoose, up until we have chosen all possible combinations. So let's go for the first solution for the problem subsets. So this solution was kindly submitted by Jize Zhang in April 13, 2020, with 97% faster than every other online submission for subsets. And it basically exactly shows those patterns that we've just discussed. What you usually see is that you have like a main routine that's being called, and you have a helper routine that's being called. The main routine sets up everything that we need in order to call the helper routine, and it also comes with a variable to keep track of where we actually are in our explorer. And the helper routine then gets those two parameters. It gets the vector of possible numbers, and it gets the number that we want to pass on, and that number is basically like how many items have we put already in before we have reached the length. So the key thing where we look at here is those three lines. We have pushback, helper, and popback. Helper here being called within helper, so that's the recursion step. So whenever we are not at I equals length, whenever we've not explored the full range of numbers in that set of numbers, we will go in here. And in here we basically using a vector, current numbers, and pushing back the value of our nums vector, which is initialized at the very beginning with all those numbers that we put in. Like if we put in the numbers 1 to 3, it's initialized as 1 to 3. We're going in here, and wherever we are with our number I, we are putting that element on top of current numbers. And then again, we call helper with our input set, with our input vectors, and with the next element in the vector, up until we have reached the final length. And then when we're there, we're popping that back from our stack of numbers, of current numbers. And popping it back, and then we're calling helper one last time. And that's basically the whole theme to backtracking, as we have just discussed beforehand. Select, explore, unselect, or choose, explore, unchoose. Okay, let's see the next solution, where we basically find the same pattern. A simple backtracking solution provided by Haldia, April 9th, 2020, for the subsets number 2. Again, we have like a main routine that calls backtrack, and in backtrack, backtrack calls itself. And sure enough, we see that pattern again. Choose, temp pushback, backtrack, and temp pop again. Those are the three steps again. We're choosing an item, we're exploring it with backtrack again, and then we're popping it again. Let's go to the next example. This one is the permutations, how many unique permutations we can get, with a main function that returns the vector of vectors, or the vector of all different permutations. And it calls a helper function that keeps track of the numbers that we still want to explore. An index that keeps track where we are in that vector, and finally we want to return on ordering. So here, kindly enough, the person YY0125 has selected to comment exactly those three key steps: choose, explore, and unchoose, right? And in permute helper, basically all we do is check if we have already reached the final amount of elements in our vector. If so, we just return our current ordering and put it back to our final solution, which here is a member variable of class solution. Otherwise, we go through all the elements that are still left in the vector, like from I equals the index that we put in our current backtracking call, and then go from there all the way to the end of the vector and increment that index. Then we choose the next number from nums and put it back onto our current ordering vector, which we then call again. So we update that element in the vector, and then we call permute helper with the index increased such that we get closer to the end. And then when we're done with calling, we are unchoosing that item again. And we swap. Okay, let's see to the next solution if we find that same pattern. Right here, pushback, backtracking, popback in a helper function backtracking that's being called by the main function permute unique. We put in the vector of int and we return a vector of int. And the key thing here is basically that we need to sort first. And we go backtracking. And in backtracking, we do the same thing. Push a current element onto a temporary vector, explore backtracking with an updated index, and then pop it back from that temporary vector. Right. And since this is like the more complex permutations solution, we actually need to keep track of the logic here, which is expressed in this if condition. And we also need to make sure that we keep track of which elements we have already visited and we have not visited in order to get the correct amount of duplicates in there. Next solution is the combination sum, like the target integer value and the vector of integer candidates. And again, for backtracking, we see pushback, call to the backtracking function, and popback. So as you can see, that pattern emerges here again. From a vector of sub-candidates, we draw and put it back onto our solution. Then we call ourselves, and then we pop it back from the solution. And whenever we have reached our target, which is the current sum equals the target, then we actually take that as a valid solution, our backtracking search, and put it onto our vector of vector int answers, we push the current selection of numbers. Okay, let's go to the final problem that we are discussing here. That's the palindrome of strings. Let's see where the pattern emerges here. The pattern emerges here in the function palindromes, calls with a string, the index again, vector of substrings, and here basically the submission keeps track of the result as a parameter that's being passed in by reference. And here again, our termination condition is if we have reached the length of the vector, then we just push back the result. Otherwise, if we have not reached the vector, then we call another helper function if palindrome. That's basically here just checks if the word satisfies the condition of being a palindrome, which means if it is mirroring, like you can swap it and then it's the same word, right? So if that's the case, then we will push it back onto the substring and make sure that we have the correct index range for our substring, and call the palindromes for the updated range. And the updated range here again is the index being updated. And once that search is done, we pop it again from our substring. And then the final result is being kept track of in that pass by reference variable result. That is then been passed on as the solution. And the setup and call basically all takes part here in partition. We set up an empty vector of string result, set up an empty vector of string substring, and call palindromes with our input string, the index 0, the substring, and the result.